Hello, welcome back to the course in January 2023. So today I'll begin with the lecture about sequence generation, which connects to a lot of work that we've mentioned earlier. And I actually decided to take a video I had done for the summer school. It's quite good, and the recording is good. And so I'll transition here to that video in a moment. And at the end of the video, I'll add a little commentary. So occasionally you will hear in that video references to the summer school, to other events in summer school. So please ignore those. Thought it's better than just to record something exactly again, the same thing again. So I'll switch to that and then talk to you at the end of the lecture. Sequences. And I emphasized already in the first two core lectures that a lot of the things that we were looking at actually involve sequences. You saw that these cognitive architectures that did grounding go through multiple steps. We even looked at an example of hypothesis testing where the system was first selecting one object and then discards that object and selects another object. And my claim was that all of this happens autonomously. That's where the title comes from of today's lecture, autonomous, that is driven from within that system by its own resources, not paced externally by stimuli and certainly not by a computer clock that says at a certain time you load something into a processor and so on. And I think it's a moment's reflection, and a psychology textbook will reveal that pretty much everything we do consists of sequences of individual acts, mental acts, physical acts, elementary movements, movement acts chain together make our behavior, and mental acts chain together make our thinking, our speaking, our listening, our attending, and so on. All of these are sequences. And that's, of course, one of the reasons why people have thought of cognition as a form of computation, took from the computer metaphor that idea that a computer has a clock and operates on instructions one after another and so on. And has not really thinking very deeply about exactly how that happens in time in this wet thing that we have up there that's called the brain. So there are a few cases where these sequences are really fixed and rigid. These would be skills. I mean, when you grasp a glass, you don't think about, oh, extend hand and now begin to draw in the fingers, right? So there's some fixed sequential actions, highly trained patterns are like that. But in many cases, of course, that these sequences are very flexible. In language, that would be the most extreme. Presumably, I'm not saying the exact same thing I said before. In my case, you might have some doubts about that. But in general, of course, we assemble sequences of thoughts and of actions and of words that are very variable. This is this property that's sometimes called productivity in cognitive science, that you're able to make arbitrarily many, sometimes even a question if it's really infinite or not, different kinds of sequences. And in behavior, that's certainly true. Okay, so it's very important to understand how sequences work. Now, we want to understand, of course, how sequences work in neural terms, right? In neural processing terms, and we use DFT for that, as contrasted to just assuming that there is something, that can call a subroutine and then returns control on a computer, right? And so when we do this neurally in DFT, then we're dealing with attractor states. We're hypothesizing that the neural states that are instrumental in bringing about a particular behavior or a particular mental process are governed by neurodynamics that have attractor states. And we have these arguments that that's necessary ultimately for linking these processes up to the sensory motor surface. And attractor states resist change, right? And in a sequence, you're changing state from one step to the next, right? So there is a conflict between these two constraints, to change and to resist change. And the answer, of course, will be that we will have to give up stability to enable change. So we'll have to induce instabilities in a targeted way. And you're familiar from the previous lectures with the candidate instabilities that we can use. So we'll use instabilities to selectively and systematically destabilize the state that we want to end, and then enable reaching a new state that will be the next step. And I'll take you through an example for that, and then I'll talk a little bit about the general mathematical idea behind that. I'm not doing that very abstractly. So this example is a physical example of a sequence of physical acts. It's actually a form of visual search, but for an agent that moves around an environment. In the experiment, it's actually a little robot that uses the kind of dynamics that I present in the first lecture, and it avoids obstacles, and that makes it actually, I didn't explain how that works, but it's also a very simple thing. And as a result, it meanders around the environment, and in this environment, there will be objects of different colors. Again, we always use these very simple feature values. And the task of the vehicle will be to visit these objects or search for these objects in a particular order in terms of the color. That is, first find a blue one, then a red one, and the third, I'm missing here, the number 3, then find a green one, for instance. And that will take variable amounts of time. This vehicle doesn't have a real map of the environment, so it will have to search and takes time. And so we're this is designed to exactly probe that problem, that you want to have stability to achieve your goal. So you don't want to, for instance, go to the red object just because you happen to pass by a red object. So when you go by a red object and that's not your current goal, then you don't want to destabilize your red. You want to keep your red intention going. And then, but then at some later point, when you have achieved red, then you should be open, for instance, to go to a green object. So the concrete implementation of this was the topic of Julia Sandomierska's doctoral dissertation published in 2010. And she had actually a scenario in which she did both things autonomously, that is defining the sequence and then acting out the sequence. So the defining was based on learning. She was actually here showing to this little robot, the camera is pointing in the direction of her hand, showing it objects of a certain color in a certain order. I think it's yellow now, red, and then she's showing the robot green, blue, and again red. And there's a little subtlety you see at the end of showing a cube, she moves it a little closer to the camera. That actually indicates to the robot that this step is finished and it should learn the next one. I'll show you how that works in a moment. And then she sets up this arena. Right? I didn't film that, but she sets it up in a new form. So this robot doesn't know about any of the spatial layout, and the robot just wanders around avoiding obstacles more or less. And as a result, it somewhat samples the scene. So it actually approached the yellow. So it's programmed to, when it finds an object on its sensory surface, it actually moves there until it's really large on the sensory surface. And then it's done and moves somewhere else. And it will, for instance, I don't know what it's actually currently looking for. So we'll solve this task. And I wanted to show you here on the next slide, particular contrast. So this is the robot passing by the red when it was actually looking for some other color. And so it was ignoring the red. Well, this is somewhere later in the sequence when the robot is actually really aiming at red. And then it drives close to red and then actually moves on as it switches. So this sort of demonstrates that the system can be selectively attentive to what is current task, stabilize that task, and ignore distractors. And then only when the task is done will it be again open to objects of that other kind of color. So the core idea that we invented around that time that has since become a real cornerstone of DFT. You see in the book, it's actually the second to last chapter. So it sort of was the most advanced for some time, but now we've moved way beyond that. We use this everywhere. So this idea is what we call the condition of satisfaction. The term was actually adopted from John Searle's theory of intentionality. And there's a project that Jan Tekulve actually did his PhD thesis on to really push that. And he will talk about that on Friday, push that analogy to intentionality. So here, this was, I'll just take that word for now, and we'll see more about that later. So the idea of that is that when you have a certain action plan. Here we call that actually an intention to find, let's say, a green object. That action plan makes a prediction about what the sensory outcome of realizing that action plan would be. That's this little arrow makes a prediction, and that prediction activates a neural representation we call the condition of satisfaction. It's a neural representation of that. That prediction alone is not enough to induce a peak, but then you have, act out the action, you have some way of realizing that goal, and then you get some visual information in this case, or sensory information, and that percept would provide input to the condition of satisfaction. And if it matches this prediction, so where the peaks overlap, for instance, so the inputs overlap, then a peak is generated in the condition of satisfaction field, and that would be then the trigger of an instability. It would actually inhibit, here it goes to another layer, I'll explain that later, but ultimately what it does, it inhibits this peak, and therefore ends that state. So inhibits means you go through the reverse detection instability, and then in fact what will happen is that because there's no peak anymore, there's no prediction, and then also this year will decay. Before I go into the math details of that, let me illustrate that for you. So this system is actually doing a form of visual search that you're familiar with now. It is a one-dimensional search in one-dimensional space, because we're only interested in the angular dimension, so the direction, for heading direction, right? And therefore we're summing actually all the inputs along a vertical column, and what we're doing is actually computing a color histogram. So over color, we're looking how many entries there are at different hue values. For instance, if you look at this element here, you will get a lot of white, which will not contribute to the hue space, and then you'll have a lot of entries in yellow, and that will give a nice peak in yellow. So that's the sensory information you get about color, and visual search will essentially erect a ramp, a ridge-like input at the search color. For instance, if it was yellow, it will be a ridge along the color dimension localized at yellow, and homogeneous along space that would be overlaid with the kinds of inputs I just showed you. So the different spatial orientations, so the different columns in the visual array of the camera. You have this histogram across color. So this peak here would be, or this input here would be the result of an input like that. That's how the visual search is realized on that vehicle. So it's not making eye movement, it's actually moving around, both turning and driving around. And that's the form of visual search. It's literally a search of a vehicle, random walking here. So here is sort of an overall summary of what happens here. So your intention, so we have the special case that the intention and the outcome are the same. That's like the trivial example we used to establish the idea. So here, your intention is to find a certain color, and your condition of satisfaction is to see that color, right? Color to color, very simple. Of course, in general, this would be much more flexible. You could say maybe my intention is to grasp an object, and my visual feedback will be maybe to see the object in my hand, or to have some haptic input about that, or to have some proprioceptive information about tension in your muscles that you're exerting force on a surface and so on. So you would have multimodal and effects that will potentially be quite different from the shape that the motor intention takes, or the action intention takes. So we just took this trivial example to make things simple and easy to demonstrate. So the intention is a particular peak in an intention field at a particular color value that guides, as I just hinted, visual search. And in this visual search, there's constantly a chance to take any of these inputs. The different objects are 2D inputs into the color space field. Remember, we're just using one spatial dimension, the orientation dimension, so we're summing across the vertical. So these little peaks here are entries directly from the visual array. This would be 2D entries, bound in the sense I explained yesterday. And then through the ridge, I'm fishing out any localized peak of activation, fishing out any 2D input that overlaps with that cue. And then a peak forms. And when a peak forms, there's actually another behavior that isn't explained here. Then the system actually really, there's a peak generated in a target field, the heading direction is attracted to that, and the vehicle moves toward the object like that. That's how that peak will be, the visual object become large on the sensory array, and large means it extends along the vertical, and there will be a lot of entries into the histogram. So as a result, what happens is that ultimately there will be a lot of a large amplitude here in the input strength, and that supports this perceptual. So there's a graded measure of perception. So then you will get a large peak in this perceptual field. And that perceptual input is provided to the condition of satisfaction representation, which is pre-shaped or pre-activated, by the intentional input. So this is the pre-activation, and now a peak hasn't formed yet here, but once enough input has been perceived here and that overlaps with this peak, then the condition of satisfaction generates a peak. I have some videos that I assembled from Julia that illustrate the time course of this, and there's a slight difference in the system, so I'm not explaining that. So here's an intention, for instance, that creates this ridge in the search field. The condition of satisfaction is here, just one neuron representing that entire field, and at some point here, I guess right now, a peak was formed, and the condition of satisfaction fires, and actually here, it's separate fields of different intentions. So this first field was deleted, and the next field was activated. I didn't explain how that happens. And so another search, actually there was another condition of satisfaction here. Again, this hasn't fired yet. This isn't large enough. See the inputs as the vehicle is walking around, there's some inputs walk around. And at some point, these inputs will overlap here enough with that ridge right now. And when that peak is large enough, it fires a condition of satisfaction, resetting and charging a new, so inhibiting and charging a new intentional states. So I'm showing this, some of the details here are different, like I didn't explain this here, the ordinal stack. But for you to get a sense that now really events happen, right? These events happen when a match is detected. And you see it's not equidistant, it takes a different amount of time to reach these different objects of the corresponding colors. Now, this is how now the system does sequential stuff, right? We make these events happen, and these events trigger changes in the system that then activate the next state, and that's based on making targeted instabilities. Here is a illustration of just one of those transitions. So here is the intention field. So there's a peak at whatever color that is, I don't remember. And there is some neuron that represents what, where you are in the sequence. I haven't explained that yet. And the condition of satisfaction is pre-activated. This is the yellow is sort of an intermediate level of activation, not yet a peak. While here, this red one is a real peak. And this is when the condition of satisfaction signal comes in. The peak is being formed here. That peak drives inhibition of these intentional systems, and that ultimately inhibits away the current intention. And then as that goes away, then the condition of satisfaction also decays. And then actually, in this case, the next system here, the blue is the next node. I haven't explained yet how that works. The next blue node comes up, the previous one stays off, and the next color is loaded here into the intention. So in effect, this is how the system, this again, just from some run, shows here which intention is activated. It shows, I believe this is the condition of satisfaction, and this is something about where in the image the corresponding state is. And so the important point is that you see that the system is taking different amounts of time, and within these intervals, it is stably focused on its task, is looking for the expected color. And then when it condition of satisfaction fires, it is able to switch to the next task. So it shows the different orders that it does in. And actually, during the learning stage, the same happens in the learning stage. And this is why Julia was actually moving the objects closer to the camera, because that would make the color peak large and would switch a condition of satisfaction. So it's a learning mode in which it's not a where it's really just the condition of satisfaction is really just triggered by a large monocolor peak in the perceptual field. And then the next node is open to learning. It's actually learning through having learning what color is associated with the next step. And again, this association and how to select the next one, I will explain a little later. In her learning trials, it's a bit more rhythmic because you're sort of presenting this as somewhat of a rhythm, but it's not precisely rhythmic. So sometimes she held it a little longer, sometimes less long. So that's the main feature, this ability to have stable states as long as required and only then move on, right? So if you think of other ways of doing this, where you would have some kind of schedule, a lot of models of serial order, for instance, were based on that, an idea that one neuron triggers the next. And that works if you have just transients in the brain and in a network, for instance, a famous model has that, one population is the next on chaining system. And that only works if it's not connected to anything real, or these processes are all the same. They all take the same amount of time. And we do a lot of sequential things rhythmically if we can, but it's quite critical that we don't always do that. Playing the piano would be very boring if you had to make all the intervals exactly the same, right? Good, so that's illustrates most of the ideas. And essentially what we are doing in general is we're doing the same sort of thing when we're making a purely mental sequence, when it's not physical. So what the general mathematical mechanism is summarized here. So what I just showed you, you have some representation of what your intention is. That could be a motor intention, or it could be also an intention to create a particular mental state. For instance, when you do mental arithmetic, right, to create a step, or to the examples that we had where you try to enter something into memory. I'll show you an example from Jan's work a little later, where you see some peak is creating a work in memory, and that was the intentional act. And once you've done that, you can go on to the next item. Excuse me. So that's intention that makes a prediction. This is a different dimension, y, and so that pre-shapes the activation. It will be like a below a peak. And then if you get a signal through the world, as the example I just showed you, through some perceptual state, that could then trigger a detection instability here that could create a peak. And because this field or node is inhibitorily coupled to this intention, it will, once there is a detection instability, it will create a reverse detection instability on this field. So this peak will go below 0. And therefore the prediction will fall away. And if you arrange things correctly, then if the prediction falls away, even in the presence of a suprastate, a suprathreshold input from this one, you can go push this through the reverse detection instability. So then both of these peaks are gone and you're done with that intention. And so which intention comes up next would be then decided by something that I'll discuss in a moment. So we showed the example where it goes through the world, but you could also really have a signal from some other neural representation. I'll show you an example later where you're looking at what happens in a target representation. That's not these two fields. This just is a text that explains what I just said. In some sense, this is related to what some of you might know as efference copy. Excuse me one more time. So the notion of efference copy is also an idea that if you have a motor command that you're predicting the sensor information that would be expected when that motor action is performed, and in the literature of this efference copy, so is sort of a more general concept than reafference. So you might have heard about the reafference principle. Goes back to von Holst and Mittelstädt. That the difference is it also acts inhibitorily, but in the general thought of efference copy thinking, the inhibitory effect is on a perceptual representation. That is, you're not perceiving perceptual effects that are caused by your movement, so that are not surprising in some sense. And so that's related. Here, we're looking at an inhibitor, in fact, on the motor intention. And it's not excluded that some of the cases where people talked about reference were actually including a motor component. I think it would be interesting to look back at some of that literature in that light, but it's not always been studied, of course, in that way. So it might be related to this idea of free efference or efference copy. So a lot of the examples that I showed you yesterday contain ideas like that. Is somewhere in there was a subpopulation of the architecture that acted as a condition of satisfaction, that is, that inhibited the originating state when it was activated, and its activation was conditional on some component of prediction from the intention. So it's not always that explicitly there's one field of one nature and another field of another nature. It's more the neural principle that that the sketch here is supposed to illustrate, and it is realized in different architectures in different forms. So, for instance, in some of our architectures, we're now using a more sophisticated form of that, a sort of general principle of mismatch or change detection. And in the book, there is a chapter on change detection, which I believe is maybe chapter 6. And this here is actually a generalization of that. So I'll not explain that in a lot of detail, just to say, this will be an example where you have two things to match. For instance, you're attending to a certain feature and you have a prediction about what feature you get. And then you could have, for instance, a match field, so that when these two are at the same place, a peak would be, actually this is a mismatch field. So when these two are at the same place, then one is excitatory, the other is inhibitory, so it cancels. And so when they don't match, then they don't cancel, and one of them will create a peak, and then you can combine the peak detectors. There's some neural representation that is sensitive to whether there's a peak, in order to compute from that if there's a match or a non-match, and that's how you could, more generally compute a condition of satisfaction. And the interesting thing of that is you can also compute from this a condition of dissatisfaction. That is, you could detect that there is no that the effect that you were aiming at did not come about. That is a well-known problem in cognitive psychology. So how do you know that there's a mismatch now? Maybe you didn't give enough time. Like some of you know these little visual puzzles where find the difference, right, between two images, and you have found 8, but supposedly there are 10. How do you know that they're 10? You've tried forever and didn't find the 9th and the 10th. And ultimately, there's always some idea of some kind of timeout, some kind of stopping, that you give up at some point. And there's that is a question of how much time you give yourself. And that's actually implemented generically in these sort of things, in that there is a race, there's a default, no match response. So this response will win. It takes some time for this to reach threshold. And when it wins, it will inhibit the match response. No, it's actually the other way around, right? Sorry, the no match response. Yeah, the no match response wins by default, and the match response is then inhibited by the no match response, because the match response would be based on not noticing a difference, not having a change signal. I'm not explaining that here in detail. In different models, this is used in different forms. And I don't think so it was, for instance, relevant to this hypothesis testing story. There we had a condition of dissatisfaction. So this is something that requires a little bit more discussion. I'm just giving you the perspective that there is also that other element of the opposite of condition of satisfaction. Good. So this much about that mechanism. That mechanism is very much present everywhere in our architectures. That's what makes them do sequences of things. But I've only explained one aspect of that. I've explained that you're ending a current state by making it unstable. Now we have to think about, how do you then select the next state? How do you determine what sequence to make. So one is to control it temporally, and the other is to make the selection. And that's where we're implementing ideas that are in the literature, three notions: gradient-based selection, chaining, and positional representation. I'll go through those. All three of those are used and realized in DFT, and I'll illustrate then these ideas in one integrated example. So this notion there's a review paper by Hansen and Burgess. I don't know how to pronounce this name. Is it Burgess or Burgess? In 1997. But I don't think that they invented these terms. I think these have been around for a very long time. I don't really know historically who was the first who came up with these different ideas. And so the three proposals, they weren't, of course, framed in neurodynamics, right? They were more abstractly framed in terms of some kind of abstract neural network kind of mechanisms. And there's a literature on finding behavioral evidence for these. I'll not go through all of that, but there are some arguments that all three might be realized under some conditions in very different kinds of tasks. So this is useful for serial order in perception, in thinking, but also in motor behavior. So I'll go through each in turn. So the gradient-based idea is that you have some activation patterns, for instance, could be a salience map or some input map and so on, in which different possible choices in our language will be localized in these fields. In other neural networks, maybe could be the individual neurons that stand for something, in which there's a different level of activation representing how close to you are to being selected. So you could encode the serial order in this level of activation. There are proposals, for instance, by Grossberg's group, that you could even engineer some special neural circuit that can store in working memory a level of activation. So a neuron firing a lot for the first and firing less for the second and less for the third. These are, again, there's some arguments that might exist. These are sometimes called line attractors. They are inherently not stable, marginally stable. It's not totally excluded that could happen. I believe it is, if it happens, it's a very special kind of mechanism. It's much more commonly relevant for selection that's input-driven. For instance, in our visual search system, after you're done with one entry, you will be selecting another one, and that other one would be the most salient, other than the one you just had. It's actually that inhibition of return that we're using to delete the item you just looked at. Right? If you looked at this item previously have a representation in an inhibition of return field, it's a working memory of that, of having been there, that then inhibits that item. And so the next most salient item that has most input would be selected, right? So it's that's a very common form of how this happens in the architectures. I showed in all three architectures, this is used somewhere. One could think of that as also being sort of very general kind of idea for mental activity, and it's actually in some less neurally realistic form. Even classical cognitive architectures use an idea like that. That is, that you would have some form of competition between possible mental acts or mental operations, and they would get some. They would have an activation variable that represents whether they are being executed or not, and that when you're selecting your next one, you're adding all the inputs that they get, all the votes for each activity, and then you would select the one with the most votes. So you could think of, when I'm speaking, I'm maybe context and thought and some linguistic rules and so on would all pre-activate certain things I could say, and then one of those will win. And that will be gradient based on that. The one that wins is the one that gets most inputs, for instance. So that's a very general idea. Chaining is a bit much more specific kind of idea. And there is actually reasonable evidence for chaining in sort of fixed sequences that you have learned. And so what the idea in chaining would be that there is some kind of directional coupling, so that one node would be when it's active, it would pre-activate a subsequent node, and when you have somehow arranged that's not accounted for in the classical thinking for the previous node to go off, then the next node is activated because it was biased by this directional coupling. So, so that as a general idea is less flexible, you can imagine. You know, if you have chaining, the main difficulty of chaining is that you have to do some special gymnastics if you have a sequence in which one thing happens twice. For instance, the example I just showed you, there were maybe, I think there were maybe red objects in two positions in the serial order, and therefore you would have to represent that this is red in that first case followed by green, let's say, versus red followed by blue, because in the chaining idea, once you activate a particular behavior, then it uniquely points out what the successor behavior is. And so there wouldn't be a possibility to have two different successor behaviors. And there have been some proposals for workarounds, like having multiple copies of everything, but you can see that that might be a little bit more problematic. But there's some evidence for ideas like that when it comes to fixed action patterns, for instance. We're using this in some of our architectures exactly to explain cases where there's a systematic preference to perform certain things in certain orders. So for instance, in the relational architecture, we hypothesized a particular order in some cases. The neural way we do that is that we have, these are always pairs intention, conditional satisfaction nodes, and there would be this form of double inhibition. This is called a precondition neuron in our jargon. So when that precondition neuron is active, it is inhibiting the intentions it is projecting on. And this condition of satisfaction inhibits this precondition neuron. The precondition neuron is on by default. So when that is inhibited, it releases this downstream action from inhibition. So in that sense, when you're done with this one, the next one has a chance to become activated. And by having descending inputs, you can sort of select which intentions you pre-activate to be potentially activated, and then the chain sort of releases every node when its predecessor is done. So that's used in some of our robot, for instance, reaching activity, and a couple of systems like that, like in some of our action architectures, which we don't really explain here. There is, for instance, a fixed sequence that you have to first have an object selected potentially before you can make it a target of a reaching movement, right? Which is sort of logically unique in its serial order. You don't want to reach first and then select the object, right? It doesn't make sense. Good. Now, the most interesting one is the positional representation, which in a sense combines the chaining idea with a much more general idea of neurally representing the contents. So the contents of individual nodes is free. So there would be an idea that you have some form of chaining mechanism. We call this an ordinal representation. So some nodes which are arranged as one possible arrangement to provide a chaining mechanism. So for instance, in the sort of a generic form, there's multiple ways to realize that generic form. Each intentional node here activates a memory node. So this node will remain activated when its inducing intentional node is off. So for instance, when this node is on, it activates this memory node. And then when this goes off, the memory node stays on, and each memory node points to the successor intentional node. So this node on means this intentional node is a little bit activated. While this one is activated, it's not winning. This is globally inhibiting. But when this node is inhibited, or actually the whole system is inhibited and then released from inhibition, then this node has an advantage because it's activated from this node, and that will mean on the next step, this node gets activated. So this is a possible very simple form of chaining. And then the notion would be that what these nodes represent, that is learned. And this is how Julia did this. So for instance, when this node is active, it has synaptic connections to, for instance, sort of a color field or action field. And through Hebbian learning, it would associate its activation with this contents. And then you see this is much more flexible. You're pointing. You have a positional representation of the order. That's why we talk about ordinal nodes. It's sort of like a dimension, but it is sort of discrete in organization. And that can then learn any projection onto other feature dimensions. So this was at the core of one version of what I showed you. And there, these ordinal nodes were pointing at these action fields and each, to different locations. They were essentially becoming concept nodes through that. They were pointing to a condition of satisfaction field. In this case, this was very simple, but we also showed how you could learn conditions of satisfaction. And then the intention field was, driving the motor system, in some closed loop, and then also driving the condition of satisfaction perception, which would trigger here the detection of match. And when that happens, the whole ordinal system was inhibited, this intentional layer. And when that happens, this goes away, the peak goes away. And then when it's released from inhibition, because the condition of satisfaction goes away, then this will switch one to the right, one ordinal node on, because this will bias the selection, and when the inhibition is disappearing here, will bias this node to be selected. That's how that worked. So that's very flexible, and it's often been invoked as the most general principle of serial order. Serial order expresses that the ordering of items can be varied somewhat freely. There might be constraints like grammatical constraints, that certain categories have to come in different places. But overall, that you're able to assemble any sequence as long, consistent with some grammatical rules for action or for thinking or for language and so on. And so the system is also very good for learning, because it's a very, very clear place where you put the learning here into these connections. And the other two, that's a little less obvious. The limitations of this are clearly that if you think about this as learning, then of course you have to have the projections, right? There must be some substrate for that. So these neurons must be projected to something. And it could be a problem if you have some neurons that are selected to just about anything in the brain. There is actually a serious talk about systems like that in hippocampus. And one of my colleagues here in Bochum has a hypothesis that something like that is at the basis of the so-called pre-play feature. Then you have hippocampal activation that is observed, for instance, when a rat navigates in a lab, and there's what is called replay, where you see that same sequence of activation hippocampus when the animal is sleeping, is dreaming. It can be sometimes backward, sometimes forward. And there's also, so that could be thought of, running through what you did when you were connected to the world, just in simulation. But the astounding thing, there's also so-called pre-play, where you see activation patterns in hippocampus that you will later, once the animal has learned to navigate in the labyrinth, you will see the same sequence that you saw when they were sleeping before that experience. This is certainly astounding. And so that hints that the machine that does the sequence is actually fixed. And when the animal navigates, it associates that with particular events out in the world. And so the sequence that you're seeing is really that fixed sequence that the hippocampus circus has at its disposal. This is not far from proven. This is just a thought, and I don't follow that literature so closely. I don't know exactly where that stands, but that could be a possible neural substrate for this. Hippocampus would be a very good place for this, because hippocampus is famous for being connected to so many different cortical areas. So this idea of having enough neural substrate to link up through Hebbian learning to the contents of your sequence makes some sense. Good. So that's the three principles of how you select them. So let me show you this architecture that illustrates all of that. It's the same sort of thing. It's essentially a modern version of Julia's wandering robot. And this was done by Jantje Kulve with a visitor we had at the lab. And we published that in Neurorobotics. It's this is the architecture. I'll show you that in a moment. Let me first explain maybe the task. It's analogous to your assessment that you show this robot colors in a certain order. This is simulation. And then you arrange these colors on the table in a particular way, and the robot, in this case, points at the different targets. So this takes away this whole issue of navigating and mapping and estimating where you are. This is all based on representations that way you know where you are, and it's much more closely associated to the visual representations. You will see again tomorrow when Raul presents that, or that are already presupposed in these grounding examples. So if you look at the architecture, it has essentially a form of scene representation that you build a simple version of, right? The camera, again, color-based. I think we also had maybe only color, I don't remember. I think we had only color as a feature dimension, very simple. So you have these color space representations, and assemble again a working memory of that. And so that's where the contents lies. And then you have a movement architecture where you have a project, I believe, on that some of you might be able to do that drives the arm to a target that you have selected. So the target representation would be informed then by the scene memory. And up there is the serial order machine. This is the serial of these ordinal nodes, and these are the memory nodes that always activate the successor. And that machine would be informed about color, the color that is subscribed, the concept of color, and the color that then influences the motor behavior. And you would have a phase where you learn, that is, you learn the projection onto a particular color that would be then based on the color that you're currently attending to in the learning phase. And then in the recall phase, you would be exploiting these plastic connections to find out what color you should currently direct your attention at. And so here's an example of the learning. So the different ordinal nodes are, the color code is associated with which color they end up being for. So for instance, node number 1 was active initially, all the other nodes are subthreshold. When the object that's green is presented, and you have to, again, you have to see it's the only stating object, you have to have detectors that detect that something changed is now in the visual array or is removed from the visual array. And the color is greenish here. And then the learning establishes the weight between ordinal node number 1 and this green color. And the fact that this is turned off triggers the offset detector in this frame. And that switches, that makes a condition of satisfaction for the previous state. And that switches now on the next node, the node number 2, which a moment later is, this object is presented to it. And that will lead to learning that connection between the second node and blue. And again, the offset of this blue triggers the transition to the next node. And here it actually takes much longer for some reason for the learning to saturate here and so on. So that's how you learn. And you're doing this here at the bottom is really using Heppian learning between the ordinal node and that the particular color representation. This is how this model builds the scene. So you presented the system with a scene like that. This is analogous to what I showed. Did I actually show that? Well, I guess with what you, I don't know, did you actually do that? No, you didn't. So you will be, some of you will be building a system like that. So you're seeing the scene here, the salience. And in the scene, the system is actually sequentially selecting objects. So it's selecting here the pink objects. That would be this intention that shows there is a intention selection. So that's the perceived color. Here is your memory stack in which there are these columns at locations at which there is some input. I guess this broad one must be the arm, and there's some way to deal with that. Its color being ignored. And so now your attention is selecting this, and what you then do is you put this into working memory, and that so there's a peak being formed here. I don't know exactly at one. I think here at this column, the intersection of this color slice with that column makes an entry here. So you commit to your scene memory that at this location there is a, what is that, a pink object, and the color match field is sensitive to whether you're extracting the color that you stored here in the memory representation of color, and you're essentially looking if this color matches the color you're currently attending to. And when that's the case, you have a match, and that enables you to suppress that attentional selection. In the visual return, make sure that you don't select it again. So this happens here. This is when the condition of satisfaction. This is an example of a condition of satisfaction of a mental state, right? It's that you've entered it into the right thing into your visual scene memory. It's not a physical state. And that then allows the system to select the next item, which will be, intentionally will be this item here, just based on status. And again, you have blue, and you select the in memory, I don't know, it's this one here that is selected. So the memory is put in here. You have blue in the memory that matches the attended blue, and you fire the condition of satisfaction, and then ultimately select some other item. I guess must be the green one. That's how the memory is built. Again, it's using these mental sequence. And you see it takes a similar amount of time, because this is now really just the time to build the peak and detect the match. And that is somewhat reproducible, but it doesn't have to be if the one peak is more intense than another, or there's some peak nearby that has some inhibitory influence. It takes a little longer to build the peak. All of those things would be stabilized again. These are these subtleties that in a lot of more schematic neural network thinking people don't really look at. And this is now how the sequence of actions is generated. So now you're recalling from memory, so activating the first node, then activates the corresponding color, which I guess must be green here. And that extracts the color position of that node, and that drives the arm to that node. And there is a position match field that creates now the condition of satisfaction for the reach, where you find out if the arm is close to, it's actually based on motor prediction of where the arm is. It's not visual prediction, I believe. And when there is a match here, that creates a condition of satisfaction for having achieved this, which inhibits all these nodes. And then the next node comes up, the second node, which is associated with the corresponding color. So the second node, I guess, comes up here, and the color seems to be blue. And you select the spatial position of blue and reach for blue, and so on. So then that's how you make the sequence of actions. Here, it's actually maybe not entirely visible, but it does take different amounts of time depending on how far the targets are. There's a cool demonstration of this on the next slide. This is a case where the same association has happened. So green is first, blue is second, and pink is third. But as the robot reaches for blue, I think, is it? Yeah, for blue, like here, the blue target is just made to jump. Sorry, I clicked on something. So the blue target jumps from this frame to that frame. It just jumps. So we just make a jump in the visual array. And so now the robot does not actually get a match. It doesn't actually reach the target. I think this must be here in this situation. And that triggers a correction movement, because now the new target is, the new target is detected. The scene representation delivers the new target. And then it makes a second movement. You see that here, it's like light blue is the motor intention. I didn't explain exactly. It's an oscillator that makes a half cycle. It's actually an active transient that makes this movement here. So usually there's just one movement per each reach. And here, this failed, and therefore is a second movement, correction movement to the target. And only then do you find the condition of satisfaction and load the next color. So here you see this is a longer trial because there had to be a correction movement, and the system doesn't forget that it is still working on the blue target, right? That's the core idea of dealing with in an embodied system with serial order. Right? That's really so. This lecture from the summer school ends somewhat abruptly because then I transitioned to other topics. So let me end the lecture here for the course by summarizing very briefly. So what this lecture was supposed to show is how the principles of dynamical field theory, and particularly existence of these stable states through local, local excitatory global inhibitory interaction, leading to these localist representations, and how they can give rise to autonomous processing, autonomous sequence generation, essentially because they can be destabilized, made unstable in a controlled way, and the conditional satisfaction is sort of the formalization of that idea. And I illustrated how this enables neurodynamic architectures to autonomously generate sequences of states, mental or motor states, which is really a fundamental step toward higher cognition. And you saw that already in some of the past lectures, and you will see this toward, for the rest of the semester, we'll be really talking about that, about how higher cognitive processes emerge from that. You will also have an opportunity to use our software to actually generate models of that nature. So I'll see you in the discussion session.